there! I thought you all are safe today. So, today I'm going to talk about WS2812. That means, yeah, simple Neo Pixels. What the case? The problem is most of the persons talking about we cannot drive these Neo Pixels using PIC Microcontrollers. What the hell is that? You think most of the things they're talking, I saw a lot of questionnaires regarding that in some sort of forums like that, some sort of YouTubers like that. They're talking you have to use higher frequency to clock speed. You have to use a CLC codes. So likewise so many things thinking. Most of the case, most of the persons are talking we have to use some sort of a AVRO at mill time. Likewise Arduino something to run up these Neo Pixels. What the hell is man? Just you can use PIC microcontrollers. It's very easy. Any PIC? Yeah, 12F, 16F, 18F. No problem. You don't need any CLC. That means code logic cells, right? Configurable logic cells. You don't need that one. Just you can use your simple codes. Can we use for loops, while loops, any other kind of delay loops? Yeah, simple. If you want to drive any LED, like any sort of a code, you can apply in PIC microcontrollers as well. Most of the case I thought you have to use a very higher clock rate, but in this case we are using simple 20 megahertz. That means if you want using 60 megahertz crystal also you can run up this like this. Okay, so let's find out. Okay, you can see this is the simple WS2812. That means Neo Pixels. Yeah, simple thing. Yeah, 5 volt data in and ground, 3 wire. Likewise here I have a 60 strips I have. So you can see like this. So this is my simple schematic. You can see what is my setup. It is a 12F675, very cheap, very reliable, very small microcontroller to run this WS2812 using this PIC microcontroller. You can see I'm using only 20 megahertz. Yeah, 20 megahertz, very simple crystal to run this Neo Pixels. Okay, so here you can see if I power up it, you can see Lucy, right here. This is the setup. Cleanly you can see here the power, 5 volt power supply using my simple power supply. No any magic, right? No any magic, no any chips, right? Okay, this is the power supply and it's coming to here. You can observe it, and here I have that data and supply VCC and ground line. 3 wires only, 3 wire communication. Right, so this is my Pixel 60 strip, right? So you can see that's a very nice code. See, there's no any type of magic at all. So likewise, very simply you can put your any code, any kind of matrix you can put into your using these PIC microcontrollers to drive these Neo Pixels. It's very simple. So what is the problem? Let's find out. Considering embedded systems, we know there are 2 types of things. One is microcontrollers and other thing is microprocessors. Simply considering the CPU architectures in the central processing unit, the one human architecture is in the CPUs, but in microcontroller CPU architecture it consists of some sort of different kind of RAM locations. Then we using hardware architectures. So considering our platform in Atmel type microcontrollers as well as PIC microcontrollers in microchips, both are using Harvard architectures. In that Harvard architectures, there are two separate type of things. One is CISC and RISC architectures. So in our microcontrollers, this microchip PIC admin both using RISC architectures. So what is this problem according to this NeoPixel driving problem? Actually, we know, I'm not going to talk about in detail of the NeoPixels. There is some sort of a 3 type of bytes to run the RGB values. So this is one NeoPixel value, right? So this one is consist of green data, and this one is consist of red data, and this one is consisting of the blue data. Likewise, GRB pattern we have to run to, that means we have to light up any one of the pixel. We can write this GRB value to that NeoPixels. So this is a 24-bit data stream, and this one is consist of 8-bit of data. Likewise is happening. So in microchip PIC microcontrollers, and considering any other, let's take AVR, something like that, at 85, likewise so things are there, Arduino, blah 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 things are there. So if we consider this one, the main problem is to write this 24-bit data. We know one bit is consist of some sort of a data logic, right? Logic 1 0, one is logic 0. Simple. But in this NeoPixels, right, we cannot write like this. We have to use another way, because there's no any easiest way to write this GRB value, because we have to use some serial data communication to enter this all data to in this pixel. To considering of this data writing, so in the WS2812, that means 2812 NeoPixels, they are giving the logic 1 is represented some sort of a timing diagram. So according to their notification, for logic 1, this one is consist of 0.4 microseconds, that means nanosecond, 400 nanoseconds. So, and this one is consist of long time, low level signal, that means 850 nanoseconds, that means 0.85 microseconds. So all the time is consist of 1.25 microseconds. So this is the problem coming to occur to here, how to write this type of one logic at once in this specific time. So that is coming with the problem. So to write this one, so like this logic 1, and this is the logic 0. Very fastly I'll talk it about this one, and this is the logic 0. So logic 0 is consist of this one is 0.85 microseconds, and this one is consist of 0.8 microsecond, and this one is 0.45 microseconds. But anyway, of this, both of the tolerance, they giving 150 nanosecond tolerance for writing this data cycle. So likewise, this is the logic 1 and logic 0. This is very simple, very unique, actually very not complex, actually very simple thing. No problem about this data streaming. So with this writing of this timing diagram, so we need 125 microsecond. So that is the problem coming. With the microcontroller, if you try to make this one using PIC microcontrollers, the problem comes this like PIC microcontrollers to run one instruction. Let's take, if you want to logic high some sort of a port, you want to write logic 1. So that is a one instruction. To execute one instruction, it needs 4 clock cycle. for clock cycles, right? In AVR type of microcontrollers, at my time, mostly to run one instruction, we need only one clock cycle. So definitely now you know this one is take 4 clock cycles, but this one is only 1 clock cycle. You can run one instruction as much fast. So with this problem, with this not the problem, with this facility, you choose AVR is one of the best thing to run this maximum light using AVR. So no, this is not the problem actually. Coming to there, let's consider how much clock cycle, that means how much clock we need to run this 125 microsecond timing data with our stream. So this is the considerable point come here, that is what is the minimum time required to write this data logics. So in here they're talking about 400 nanosecond is the lowest timing signal. With this 400 nanosecond timing, it can be vary up to plus or minus 150 nanoseconds. That means minimum value it can be, we can predict it into this one 250 nanosecond. But I'm not going to talk about 250 nanosecond, that is the least value, right? So what we can do, we have to consider 400 nanosecond for our requirement. So considering 400 nanoseconds at this time, how we can implement this timing? So one of the best method is using timer. We know every microcontrollers, most of the microcontrollers there I have separate inbuilt 2-3 type of timers, at least one. So considering that timer, and we can put to that timer and we can count down, either we can use 8-bit or some sort of things, 16-bit timers, no problem at the beginning. But in here we can consider 8-bit is more than enough, because we don't need any PLL to apply this one and select a lot of time, because we need any simple thing. So to run that timers, right, 8-bit timer, let's take, to run this timer we have to first initialize the timer, then have to set up the timer settings, then after we have to put the register clearing and interrupt routine also, as well as then we have to check that one and we have to evaluate that one, the time is over now. Likewise, so many things are there you have to do. I think mostly, definitely it should be 6 type of cycles to evaluate that one. 6 type of cycles to evaluate that one using that PIC microcontrollers. Considering problem is it take 4 over clock cycle. So let's take this one is 20 megahertz, so we can divide by like this. So the time for one instruction, to run one instruction, it's coming 200 nanoseconds, right? 200 nanoseconds. So how can consider 200 nanosecond for run this one timing cycle with this timer? It's not possible, right? Why? Because we have to run 1.25 microsecond, that is consist of like this data pattern in logic type. So this type of logic pattern you want to evaluate, you have to evaluate this type of 400 nanoseconds, 800 nanoseconds. To evaluate that one, the one instruction it takes 200 nanoseconds. To run up the timer fully, you have to use 1.2 nanoseconds, that 1200 nanoseconds, that means 1.2 microseconds to evaluate that one. So that is not possible, right? 2. If you go to count this time, but it takes 1.2 microsecond to count this time. So no, we cannot evaluate. That's the problem. That is the problem. So what is can do? We can use higher clock rate, higher fastest bit. So to do that, in AVR microcontrollers, what is going to do? In AVR microcontrollers, they're using 1 over oscillator timing. That means what is this magic? You know, PIC microcontrollers and the AVR microcontrollers also using same architecture, because the PIC is the mother one and that AVR is another some sort of another person of that separate thing in that mother, right? So 1 over oscillator clock cycle, let's take put in 20 megahertz, we can see it takes 50 nanoseconds. To add this 50 nanoseconds, that much okay, you can evaluate 400 nanoseconds without any corrupting. 50 nanosecond means you need to run 6 clock cycles, just 300 nanosecond. With that 300 nanosecond, you can just implement that one and you can run this 400 nanosecond timing as well as no problem. In the PIC microcontrollers and AVR, they are using some sort of a very trick. But already PIC microcontrollers also available, that type of thing. Some microcontrollers, not like this simple microcontrollers. In AVR simple microcontrollers, there is has some sort of a, we call phase lock loop PLL method. So 4 times PLL is available there. If you take 60 megahertz crystal, right, because that type of Arduinos, they are using 60 megahertz crystals. So 60 megahertz, they are using 4 times of higher speed up process. So up to this 64 megahertz time, very high fast frequency can achieve at one microcontroller without having 64 megahertz crystal. That means in Arduino also using that thing, there is a 60 megahertz crystal. They using 4 times PLL loop, apply that code logic, automatically it will increase the 64 times power speed of to the microcontroller. So that's how AVR is very high much. But in PIC microcontrollers also, this type of method, the 4 type of PLL also available. So now the case is coming. We can also implement this type of 60 megahertz type 4 times microcontrollers or something like that, 20 times 4 like that, but mostly it's reduced. That means it's narrowed to the 60 megahertz. We cannot evaluate much more higher frequencies. Then if you put 64 and then multiply by 4, then you can take a lot of time. It cannot be run like that microcontrollers. So nominally like this thing. Okay, so this type of 4 times PLL is the magic in this behind of the AVR and behind of the PIC. The problem is very low cost, right? Very low cost, teeny microcontrollers in AVR, they almost already have 4 times PLL mathematics. That means that magic is available there. But the problem is in PIC microcontrollers 12F, 16F, likewise things that there's no any type of this type of 4 times PLL. So one of the problem is like this, that is PIC is very over. That means over means that PIC is very older thing, but the AVR is some sort of a new thing. We know the mother is PIC, then after another person of that, after that thing is the AVR. So that's the problem coming to there. So how can I evaluate and what is the magic I will apply to remove this one? So one method is calling in microchips. You don't have any 4 PLL, but you can use higher megahertz, higher crystal method, otherwise higher oscillator to run your microcontroller. Hello, put it back. What that means? You have to use to a very high frequency, 40 megahertz. There's no 12F or 16F microcontrollers to run that much of higher frequency, and that is will narrow to another place. Otherwise, if you considering some sort of a $0.1 or something like that microcontroller and consider about that type of higher frequency microcontroller, that is not facilitate any very good at point, because we have to spend more money to make a higher frequency type of thing. So I am not liking doing like that thing. Okay, I cannot change the voltage as also this problem. So this is some sort of instruction problem, instruction execution timing problem. So what can I do? So I think to consider, read the full datasheet of the WS2812 and that means Neo Pixel datasheet. They clearly mention some sort of things to make this logic 1 and logic 0 timing diagrams. Most of the thing I didn't see any YouTube or any other forum or any other article or any other book talking about regarding this method, this magic. Actually, it's some sort of a magic. Only thing is you have to read the carefully data sheet. Everything is in this data sheet, Neo Pixel data sheet. Let's find out what. Okay, in Neo Pixels they're talking about this is that means this is logic 1. That is this one is they call as T like this, like of this pattern. They're talking about this timing diagram. So carefully look at that your data sheet. You can see something is in this thing, but this one is not exactly the timing, right? Okay, I'll put like this, right? Okay, both are same at time. So at this time you can see at some time all the both logic levels are high level and other level is logic 0, right? This high, sometimes both are high, so that means sometimes both are low. At the run of this 1.25 microsecond with your 8-bit data stream with your 24-bit total data, right? 24-bit total data. After this, you want to stop the bus, or if you want to light up that data value in your any other pixel, what you want to do, they're talking about resetting timing. You have to put your that means your data line, data pin, put to logic 0. That means exactly volt 0, not this logic, right? Not this logic, only logic 0. That means no input for the logic pin. More than or equal 50 microsecond. Did you get the point? Now to reset, put the low to your data pin more than 50 microsecond. Did you get it? That's the problem. That is the magic. They're using reset method. Then what is the opposite one? What is the opposite one? This is for resetting. What is the opposite one? Yes, you're right. Then use it. Just simply use it. How you can hold the data? Don't put anything. Don't say anything. Don't light up anything. Likewise, how can hold? This is for reset. That means reset means all are finished. Now you can light up. All are finished. Now you can light up. What is the hold? What is the method to hold? You got it now. That one. Apply that one to there. I'm not going to talk about that one indirectly. You have to think that the point. Everything is mentioned in the datasheet, but the problem is you are looking lot of things how to make this 400 nanosecond timing. Likewise things on. But one instruction we have in microcontroller, PIC microcontroller, we see 20 megahertz, we have 200 nanosecond. So using 2 clock cycles, we can evaluate 400 nanosecond timing. That's very simple. So apply any other some sort of a code to that one. how to evaluate that one. Just you can use the port high logic, port low logic, likewise thing, or any other some sort of a no operation logic also. You can put that one, and you can make that, you can evaluate that one, that timing, specific timing. So you have 150 nanosecond total difference. So don't care about that 850, likewise 50 points. Don't think about that one, because we don't have that AVR much type of higher 4 time of PLL. So then we cannot evaluate 50 nanosecond of something like that. So don't think about. We have actually 200 nanosecond minimum clock cycle. So very instruction cycle, not clock cycle, instruction cycle. So that is the way. So now we have, this is, let's take, this is my pixel, right? So this pixel consists of 3 wires, no, plus VDD, and this one is ground, and this one is the data. So I'm talking about this one, data type. So if you put this one to logic 0 level, that means it's resetted, and then it will light up the what are the RGB data in what you put into there. Think about the different way, think about the opposite, apply that one, then you can hold all the process. You can hold up your all the process. At the hold up your process, what you can do, you can put it, you can tell the pixel, hey pixel, you just keep it here. I will go to and do some operation with that my procedure. Then I'll finish that procedure. Then I'll come to and tell you what to next to do. Right? Did you got it? My point, right? You want to tell to pixel, don't write anything. You just keep it your data. Up to now I put your 24-bit data. Then I have to put to another data to that another pixel. That means you have 24 data, 24-bit stream to 1 pixel. So if you want to run more than pixels, then you have to put 1 pixel at a time. Then after you have to tell, don't put anything, just keep your data. I will tell you anything, something few minutes. That means that few minutes you can run your for loop or any other loop or anything. If you want to spend much of time, if you want to spend 1 second timing to put the second data to the second pixel, you can evaluate that one using that opposite method. Is that correct? You can think your mind, then you can find out ways that I am talking about, is that correct or not, right? So likewise, that type of very efficient way using this data streaming in this Neo Pixel LEDs. That's very complicated. That is not complicated. That's very that's very compressed thing, not complex. Very compressed, right? Very convenient actually, right? So like that method you can run like that. So at that story, right? What is that story? Holding time. You can run your loops. For loops? Yeah, why not? Just one for loop is taking 900 nanoseconds. Now we don't care about that one. If you want to spend 1 second, right? 1 second, no problem. Just you can write first pixel. Right, first pixel, put the data line to that thing and come into here. If you want to run loop or any other calculation or anything you want to run, evaluate that one, then come to again write the second pixel data with that timing diagram, logic level, logic 0 and logic 1 according to the Neo Pixels. Then again you can, if you want to, again you have to use a loop or something, then you have to put the data line to some sort of a thing. Then you can think about holding time and do it yourself. Likewise, simple mechanism going behind this Neo Pixel. So why we using actually AVR to do this like this? Okay, just you can use 20 megahertz with 12F pixel, 12F thing. Just you want to use, I think what's the minimum is the 4 times 400 nanosecond. You can evaluate I think 10 megahertz. Am I right? Right. That this is the minimum cycle timing. So that means you can use any 12 megahertz crystal or likewise these things, but you have to think, you have to make anyway 400 nanosecond plus or minus 150 nanosecond. With this certain range you have to use very better correct value megahertz clock frequency, because otherwise this lose, so with that certain time losing. In normally in Neo Pixel, in that data stream, there is some sort of a data line. It's monitoring what is the timing pulses high or not. Likewise, they are monitoring every time the data peak. That is the behind of this Neo Pixel data streaming, like this thing. But it's not mentioned. No, there's no anyone mentioned or anyone thinking about that one. Is that available in that behind scene? That's the problem. Everything have no. Yeah, behind scenes also. So that thing is in here. Behind scene is that one. Don't think about that timing diagrams, how to make them turn on. That is not the problem. The problem is how you can evaluate your neatness time to evaluate timing with your project, right? I thought more than enough about this video talking about Neo Pixels. Now you know that's very simple thing to do. So in according to this video, I hope to put some sort of example text file as well as to you can run your 12F PIC microcontroller, something like that. Then you can run up your code with that one. That's how the things happening. Now within now you can use 40 megahertz or 60 megahertz or any other 16F, 18F type of microcontrollers as well. But you don't know it. You don't need now any that means configurable logic cells to evaluate this type of things, and you don't want any higher crystal rate to run your microcontroller. Actually, think about if you're using higher clock rate, that means your microcontroller's power consumption is too much high. But considering this method, you don't like that, you don't need like that, right? Okay, thank you for very much looking this video.